Yeah.
We are going live in 3, 2, 1. We are live now.
Good evening, everybody. Welcome to the third session of the series of webinars, which are being conducted as a run-in to the international conference going to be held early next year on this very challenging and rapidly evolving field of inborn errors of immunity. Today in this, it is a laboratory-based webinar, and with us today is Professor Amit Rawat, who is currently professor at the Pediatric Allergy and Immunology Unit at the Department of Pediatrics, PGIMER, Chandigarh. Dr. Amit Rawat has extensive work in the field of inborn errors of immunity. He is also the current secretary of the Asia Pacific Society of Immunodeficiency, the vice president and founder member of the Indian Society of Primary Immunodeficiency. He's been working consistently in this field and has very deep interest in NGS of IEI, including antibody deficiencies, complement deficiencies, autoimmunity in CJD, and has been a speaker at many conferences on this topic. He has been honored with the BGRC Silver Jubilee Oration Award in 2018 by ICMR and the Dr. V.R. Khanolkar Oration Award in 2021 by the National Academy of Medical Sciences. These are very prestigious orations. Along with that, he has more than 300 publications and a lot of research projects funded by the DHR Government of India, ICMR, and including some by the Jeffrey Mondal Foundation. It is over to Dr. Amit to take us through how important is flow cytometry, how does it help in the diagnosis of PID, especially in today's time when probably after the screening tests, it is easy to go on to the NGS. But while he holds a lot of work in this area of NGS, he will be talking to us today about flow cytometry. So over to you, Dr. Amit. Alongside me is Dr. Kirti Vardhan, who will also be part of the faculty of today's webinar. And he will be taking the questions from the audience, and which we'll have at the end of this 40-minute session. Over to you, Dr. Amit.
Thank you, ma'am, for the kind invitation, and I'll start sharing my screen now. So just wanted to confirm the screen is visible and the slides are...
Yes.
So, good evening, and as has already been highlighted, I will be speaking about the importance of flow cytometry in the diagnostic workup for patients with primary immunodeficiency disorders, or now known as inborn errors of immunity. So before going into the topic per se, I'll just briefly talk to you about flow cytometry. So flow cytometry consists of three words: flow, that is in motion, cyto from cells, and metry for measurement. So flow cytometry is a measurement of cells which are flowing in a single file, and they're interrogated by a detection system, usually lasers. And so it is a powerful, rapid, simultaneous multiparametric analysis of a large number of cells can be done in a short duration of time. And it can be used to also be used to look at surface and intracellular proteins. And it can also be utilized to look at DNA and also RNA or cDNA. So what can be measured by flow cytometry? Of course, it can measure cell size, and mostly cells are analyzed by flow cytometry, but it need not be cells always. Nuclei can be analyzed as well, or it can be even chromosomes. Even chromosomes sorting has been done by flow cytometry. It also tells you about the internal complexity or of a cell. It can be used to study cell function. For example, in IEIs, we routinely perform a test which is known as dihydrorhodamine test, which looks at the oxidative burst of neutrophils. We can look at degranulation for HLH, and we can also look at calcium flux or a pH by flow cytometry. It can detect the presence or absence of exogenous fluorochrome if we tag antibodies with fluorochromes to look at specific molecules either on the cell surface or intracellular, with a fluorochrome, we can look at those molecules. And it also provides a relative fluorescent intensity. So you can differentiate between cells which are negative for a given marker or positive, or they are dimly positive or weakly positive. So it also provides a measure of the relative fluorescence intensity. So coming to the components of a flow cytometer, it has primarily three components: a fluidics, optics, and electronics. I'll just briefly delve into this. So this is a diagrammatic representation of the three elements. So you've got optics, which comprises of a light source, usually a laser, and then you have got different detectors which detect the scattered light, and then the electronics which converts these signals into pulses which can be interpreted for data analysis. So coming to the heart of the fluidics system is the flow cell or the flow chamber, where something which is known as a sheath fluid is pumped in by a compressor, and the sample is also injected within this sheet fluid by a sample injector, and both of them are in pressure. What is important in the fluidics is maintaining what is known as a hydrodynamic focusing. What we mean by hydrodynamic focusing is that within the sheath fluid, the cells in the sample stream, they move in a single file. So why is it important? Because you want only a single cell to hit the laser at a given point of time. You don't want two cells or multiple cells to be interrogated by a laser at a given point in time. So you want the cells to be moving in a single file. And hydrodynamic focusing ensures that your cells, the sample moves in a single cell stream, so that a single cell is interrogated by the laser at a given point in time. So this figure again shows that how hydrodynamic focusing is achieved. So you have got sheath fluid outside, and then the sample is injected within the sheath fluid, and the sample pressure is always higher than that of the sheath pressure. Coming to the optics, it comprises of four main parts. So you've got a light source. Earlier flow cytometers used to have arc lamps, but the modern flow cytometers, they usually have solid state lasers. They are high intensity and they provide monochromatic coherent light. Some of the modern flow cytometers also have light emitting diodes, which are cheaper compared to lasers. Then you have got lenses for collection, focusing the light. You've got mirrors to change the path of light. These are dichroic mirrors. And then you have got filters, which are also known as your band pass filters to collect light. So this figure here shows three kinds of band pass filters. So something which is known as a long pass. So if it is a long pass 500, it will allow light only more than 500 to pass through. It will block any light which is less than 500 nanometer. It will not allow. Similarly, a short pass 500 will not allow it will allow light only less than 500 to pass through, and not anything more than 500 nanometer. And a band pass filter is something else. So if a band pass filter is 550, it will allow light between 475 and 525 to pass through. So these are some kinds of, and when a laser, the laser hits the cell, a single cell which is moving in a single cell suspension, the lights is scattered in different directions. So what we typically measure is the forward scatter, the light which is scattered in the direction of the incident light, and we also measure scattered light at right angles. So what is known as side scatter. The side scatter, although the light is scattered at multiple angles throughout, but in side scatter, in conventional flow cytometers, we only measure it at the right angles. Whereas what we now known as, which are available, are known as spectral flow cytometer, they collect light which is scattered in all directions. So that is just a difference between your conventional flow cytometers and spectral flow cytometers. So this figure here shows you the common fluorochromes which are used in flow cytometry and their excitation and emissions maxima. And here you can see FITC has got an excitation maximum of 488 nanometer and an emission of 525. I don't want you to remember all this, but just to say that different lights have got different excitation and emission spectra. And what is also problematic in conventional flow cytometer is what is known as spectral overlap. So, I mean, all the lights, they have got something known as the emission spectrum, and the emission spectrum of different fluorochromes, they overlap. And this creates problem when we have to understand where is the signal coming from, and then we have to do something known as compensation. So this is just the technical part about fluidics and optics. Then we have got a electronic system, which is mainly comprises of photomultiplier tubes, where the signal is received, and the signal is first amplified in a preamplifier. Then whenever the signal, the laser hits a cell, a signal pulse is generated, and it has got a height, width, and area, and that is processed by a pulse processor. It is again amplified, and then what we have got something which is known as the analog digital converter. So this converts those pulses into signals which can be read by a computer, and then that's how the data is finally analyzed. So this is just to show a distribution of the normal cells in a peripheral blood. So you on the right, on the x-axis is forward scatter. So forward scatter determines the size of the cell, and the side scatter the granularity. So as you can see at the lowermost, close to the x-axis is your lymphocytes, because they've got the smallest size and they don't have hardly any cytoplasm. So they have got the lowest forward scatter and side scatter. Then you've got monocytes, which are slightly larger than the lymphocytes, and they've got somewhat some cytoplasm. So they have got the forward scatter is slightly more than lymphocytes, and also the side scatter. And then the granulocytes, which have got the highest side scatter and also the forward scatter. So these are the main cells which we see in peripheral blood. And this is without any antibody addition of any antibody which is fluorescent tagged. This is just based on forward scatter and side scatter. Then we can conjugate different antibodies and then see, and this is a single parametric display which is known as a histogram, where you can see that in these two plots that there are, in one there you can see that there's a positive population, in the second there is a positive population, but the positives are comparatively less on the panel on the right side. There are other methods of display. These are known as like two-parameter display. And the most common two-parameter display that we see commonly for flow cytometry is what is known as a dot plot. And in a dot plot, each dot represents a single cell or a single event which has been acquired by the flow cytometer. You've got other plots like your density plot, contour plot, but the most common ones that we use routinely are the dot plots and the histograms. So coming to the utility of flow cytometer in IEIs, so it is used for evaluation of IEIs which are associated with altered lymphocyte populations. It can be used for detecting defects in PIDs or IEI which are associated with defects in cell surface protein. Also for defects in IEIs associated with defects in intracellular proteins. It could also detect PIDs associated with functional defects. Additionally, now it can also be used for detecting post-transplantation chimerism. And in the age of NGS, it can be used to functionally for the functional validation of novel variants or variants of undetermined significance. And in that context, it probably has a promise of redemption of WOOs. And it can also be used in the prenatal and antenatal diagnosis in the absence of a genetic defect, although this is not a kind of a approved use of this technology. But sometimes when you don't have a genetic defect, probably you can look at a cord blood. In the cord blood, you can look for specific molecules or markers to determine whether the fetus is affected or not affected with a given abnormality. So IEIs with with altered lymphocyte populations. So you can see that absent or reduced T lymphocytes are a hallmark of severe combined immunodeficiency. And CD3 is a surface molecule which is present on T cells. And so you can stain your sample, peripheral blood sample with CD3, which is tagged to a fluorochrome. And if this is absent, these T cells are reduced or absent, then probably you can think of a severe combined immunodeficiency. Similarly, CD19 or CD20 is a marker for B cells, and absent B cells are seen in typically in X-linked agammaglobulinemia or autosomal recessive forms of hypogammaglobulinemia. Absence of NK cells can be seen in few IEIs such as GATA2 deficiency or MCM4 deficiency. In absence of monocytes, again, CD6, which can be stained with CD16, is seen in GATA2 deficiency. Evaluation of cell surface protein expressions for T lymphocytes. CD132 is a molecule which stains for the common gamma chain, and this could be reduced or absent in X-linked SCID. And then you could have CD40 ligand, which is expressed on activated T cells. This is defective in X-linked hyper IgM syndrome. HLA-DR could be absent in rare forms of MSC class 2 defects. And IL-12 receptor beta 1 or beta 2, which is present on activated cells, can be seen in some forms of Mendelian susceptibility to mycobacterial disease, which is associated with recurrent MAC infections. Coming to B lymphocytes, CD40 is present on B cells, and it could be absent in patients with autosomal recessive form of hyper IgM syndrome. And CD19 could be absent in a rare form of AR hypogammaglobulinemia. Just to mention that only CD19 would be absent, and if you do a CD20, in this case, CD20 would be present, only the CD19 would be absent in this rare form of AR hypogammaglobulinemia. And then you could look for IFN gamma R1 or R2 again on monocytes in patients with other forms of Mendelian susceptibility to mycobacterial disease. Evaluation of intercellular proteins. The classical example would be to look at BTK protein in X-linked agammaglobulinemia, VAS protein in X-linked thrombocytopenia or Wiskott-Aldrich syndrome, SAP or XIAP in X-linked lymphoproliferative syndrome, perforin in HLH, and also FOXP3, which is a transcription factor for T regulatory cells in IPEX, which is an X-linked disorder associated with immune dysregulation, polyendocrinopathy, and enteropathy. Functional defects, the most common use of flow cytometry for detecting a functional defect is by looking at oxidative or respiratory bursts in granulocytes by dihydrorhodamine assay for patients with suspected CGD. You could do a granule release assay for detecting certain forms of HLH. Cytokine production by activated T cells could be looked at. Receptor signaling defects can be looked by specific intracellular phosphoflow assays. And assessment of TLR signaling could be done by a 62L shedding assay. And this is just a list of common antibodies which are used for immunophenotyping. CD45 is a gating marker. It is also known as leukocyte common antigen. CD3 is for T lymphocytes. CD3 positive, CD4 positive are the helper T cells. CD3 positive, CD8 are the cytotoxic. CD19 or 20 could be used for B lymphocyte. CD345RA is for naive T lymphocytes. CD345RO is for memory. And then for naive B cells, they are CD19 positive and also surface IgM and surface IgD positive. And memory B cells, in contrast, they are CD3 positive and CD27 positive. And as I've already highlighted, the use of HLA-DR could also be to look at HLA-DR expression on antigen-presenting cells like B cells and lymphocytes or activated T lymphocytes. I'll come to the use of all this in the subsequent slides. So to highlight the use, I have just put some case vignettes. So the first case is a 3-month-old boy who presented with a history of recurrent pneumonia and failure to thrive. Examination showed oral thrush and bilateral crackles on chest auscultation. He had anemia. The leukocyte count was normal. And then the differentials showed 80% neutrophils, 15% platelet lymphocytes, and the platelet count was normal. And there was history of multiple early deaths, infant deaths in the family. So the absolute lymphocyte count from in this child was reduced. And when we look at the flow cytometry reports, again, as I've said, that CD45 is the marker for, it's a leukocyte common antigen. We use it as a gating marker. And what has been gated here in the first plot on the left are the lymphocytes. So as I've said already, the lymphocytes, they've got the very low side scatter. And then when we look at the different markers, the CD3 are absent, completely absent. They are nearly absent. And so the NK cells are also reduced. So this child has got absent T cells and absent NK cells, but the B cells, which are CD19 positive, they are the only cells which are present in the peripheral blood. The second case, again, is an 8-month-old boy presenting with developmental delay, jaundice, interstitial pneumonia. He had hemoglobin of, he had anemia. The total leukocyte count was normal, but there was lymphopenia. And in addition, there was thrombocytopenia, and he has got a positive CMV DNA PCR. And again, when we look at the flow cytometry here, what has been gated again in the first plot on the left-hand side is lymphocytes. So their CD45 expression is highest on the lymphocytes, and they have got very little side scatter. And then again, when you see that the CD3, which is a marker for T cells, there are no cells which are expressing CD3, and there are hardly any cells which are expressing uh, 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 CD19 is negative, so there are no T cells or B cells in this child, and the only cells which are present are NK cells. So this again is this kind of phenotype T minus, B minus, NK plus can be seen in RAG mutations. And I've just highlighted this that you can look at mate T cells, which is stained with antibodies, which is known as TCR V alpha 7.2. And in patients with RAG defects, these mate cells are markedly reduced compared to healthy controls. As you can see, these two patients with RAG defect had markedly reduced mate cells compared to healthy donors. Coming to the next case, this is a 5-month-old girl born of a third-degree consanguineous marriage, presented to ER with fever, cough, and rapid breathing. Elder sibling died at the age of 4 months. She has tachypnea. Hemoglobin is, there's anemia. TLC is normal. Lymphocyte count again is reduced. And here, when we look at the flow cytometry, again, in the first plot, the T cell have been gated. What I mean by gating is that you draw an artificial gate around your cell of interest, and then whatever you look further will be from that cluster. So we have gated the lymphocyte, and within that cluster, when we are looking at different subsets, so that the T cells are markedly reduced, but the B and the NK cells are normal. So this is a form of SCID where T cells are present, but the T cells are absent, but the B and NK are present. So there are different flavors of SCID. So this is the first one. I told you this is T minus, B plus, NK minus SCID, or what we known as, this could be because of X-linked SCID, but it also could be because of a SCID because of a JAK3 defect. Then we have got the other form of SCID, which is T minus, B minus, NK plus, and the RAG1 and RAG2 are the most common genetic defects in this. And then the third one is a T minus, B plus, NK plus SCID. And you could also have, but you could also have, and then the ADA SCID are the ones which have got very low lymphocyte counts. And as you can see here, there were hardly any cells to gate the lymphocyte. There was severe lymphopenia. It was, I think, less than 300 of, it was 300 or 400, the absolute lymphocyte count. And again, when you see proportionate wise, it looks normal, but there are hardly any cells in this. So this is a T minus, B minus, NK minus SCID. But there could be forms of SCID where there is T cells, but B cells are not there. And this can be seen in maternal engraftment or Omenn syndrome. And by doing a immunophenotyping, you not only confirm that this is a SCID, but you can also make an educated guess about the genetic etiology. So if you don't have the luxury of a panel or a exome sequencing, you can still select your genes based on the phenotype. It is not sacrosanct, but most of the times it holds true. So if it is a T minus, B plus, NK minus SCID, it is either the genetic defect would be either IL2RG or JAK3. If it is T minus, B minus, NK plus, then the common culprits would be JAK1, RAG1, RAG2, DNA ligase 4, Cerunos, or DNA ligase 4. If it's T minus, B minus, NK minus, ADA SCID or PNP, purine nucleoside phosphorylase would be the two genetic defects. And if it is T minus, B plus, and NK plus, the most common defect would be the IL7R, but you could have other defects like different subunits of the CD3, that CD3 delta, epsilon, zeta, etc. And in patients with SCID, the T cells sometimes can be normal, but the naive cells, which are CD45 RA positive, they are reduced. So in this figure, you can see that compared to the control, the CD45 RA population is decreased. And conversely, the memory cells, they are increased in these patients. You could also look at surface expression. So this was a child with IL-7R defect, and IL-7R, as you know, is the marker for that is CD127. So even without doing a genetic diagnosis, you can look at markers and then confirm your diagnosis. So this child with IL-7R defect, which was later confirmed by genetic testing, the IL-7 receptor alpha expression on the lymphocytes was markedly reduced. Similarly, you can look for CD132. This was a child with X-linked SCID where the expression of CD132 was decreased in monocytes compared to the control. The other use of HLA-DR in addition to MSC class 1 deficiency is that of Omen syndrome. So as you can see, the T cells were gated, and when we look at the HLA-DR expression in the patient, it is 85%, markedly increased. Normally, it should not be more than 10%, 10 to 12%. But in this child with Omen syndrome, the HLA-DR expression on CD3 was markedly increased. It was 85%. And it can also be looked to look at post-transplant chimerism or post-transplant engraftment. This was a child who was transplanted at PGI, and when we have looked at serial flow cytometry in this child, and as engraftment has taken place, you can see the different type markers coming up in this child. So moving on to the next case, this is an 8-month-old boy presenting with severe pneumonia, not responding to IV cyclosporins. He was given IV cotrimazole, on which he improved. Hemoglobin was slightly reduced. The total count was normal. There was neutropenia. The absolute neutrophil count was reduced. The IgG and A were low, and the IgM was high. And when we look at the flow cytometry plots here, so what we are looking at are the CD4 positive, CD69 positive. So these are activated T cells. And when we look at this marker, CD40 ligand or 154, we can see that in the patient, it is absent, whereas in the control, it is present. So even without doing a genetic test, you can be sure that this is a child with X-linked hyper IgM syndrome because the CD40 ligand expression on activated T cells is reduced. Here it is important to know to which cells you have to look for that particular marker. For example, resting T cells will not express CD154 or 40 ligand. It has to be activated T cells. And so you have to be sure that your T cells have been activated. So you stimulate your T cells with inomycin, but you have to look at the activation as well. So you have to get only the T cells which are expressing CD69, which is the activation marker. For example, if you have a child who has got an activation defect and you activate and then you look at 40 ligand, you might infer that this is actually a 40 ligand defect, whereas the defect might lie in activation. So the other group is combined immunodeficiency with associated. This was the SCID and the combined defects. So the next category is combined immunodeficiency with associated syndromic features. So this is a 2-year-old boy who has been symptomatic since 2 months of age with recurrent pneumonia, otitis media, eczema, skin bleeds, blood in stool. The elder brother died at 3 years of age with similar complaints. He has anemia. There is thrombocytopenia, and there is a decrease in mean platelet volume of 4.5 femtoliters. The IgG is reduced, the IgA is elevated, IgE is elevated, and the IgM is low. So again, in this child, we looked at the viscotalrich protein in the lymphocytes, and as you can see in the control, it is normal. The upper panel shows the control, the middle panel in the patient, and then when you look at the mother, there is a bimodal expression. So females have got random X inactivation. So female carriers will show 2 peaks, one of the normal from the normal X chromosome and the other from the inactivated one, which is abnormal. So female carriers in X-linked diseases, they will usually show 2 peaks because of this X-linked inactivation, X chromosome inactivation. So in X-linked diseases, if it was a good idea to screen the mothers if they are available. And so if this pattern is seen, you can be sure even without doing a genetic test or any other test to show that this is a X-linked disease and this is probably a viscotalrich syndrome. And this was the child who was transplanted. As you can see, before transplant, before bone marrow transplant, there was hardly any expression of BMT, and after transplant, there has been the VAS protein expression on lymphocytes has been restored. So flow cytometry can also be used to exploited to look at uh, different subsets of proteins after transplant to assess the restoration of function as well as uh, expression of different molecules or cells. So coming to the next category of predominantly antibody deficiencies. So this is a 2-year-old boy with severe pneumonia requiring prolonged IV antimicrobials. He had 2 previous admissions with pneumonia. Hemoglobin slightly reduced. The platelet count is normal. And when you look at the immunoglobulin levels, there's pan-hypogammaglobulinemia. And when we look at the lymphocyte subset, again, CD45 is the leukocyte common antigen, which has been used for gating. So the lymphocytes have been gated, and you can see that the CD3 is normal, but there are hardly any B cells. So CD19 is absent. And so even before going to uh, genetic diagnosis or to gene screening, you can look by flow cytometry. So BTK protein is expressed in B cells. It's not expressed in T cells. But in patients with XLA, you don't have B cells. So BTK protein is also expressed on platelets and monocytes. So you have to know which cells to gate and to look for that specific protein. So CD14 is a marker for monocytes. So we have gated monocytes and looked at the BTK expression in the patient and the control. And as you can see, in the middle panel from the patient, there is hardly any expression of BTK protein, whereas in the control, there is a good expression of BTK. So this indicates that this is a X-linked agammaglobulinemia because of a BTK gene defect without even resorting to genetic diagnosis. Here, there is a caveat that absent or reduced expression will confirm the diagnosis, whereas normal expression will not rule out the diagnosis. So I just want to repeat again that reduced or absent expression of these proteins will confirm the diagnosis, but whereas a normal expression will not, because the protein expression could be normal, but the function of that protein could be abnormal. So because this is not a functional assay, this is just telling you whether that protein is present or not. So the protein could be present, but could be dysfunctional. And this very often happens with missense variants. So the next antibody deficiency I've chosen for demonstration is the 28-year-old boy. This is a male who presented with recurrent diarrhea, pneumonia, and history of significant weight loss. On examination, he had clubbing and coarse crackles on chest auscultation. He has anemia with he has slight he had normal leukocyte count with slight with neutrophilic preponderance. The platelet count was on the lower side. Absolute lymphocyte count was normal. And again, he has got pan-hypogammaglobulinemia. All the 3 immunoglobulin isotypes, the G, A, and M are reduced, and the chest CT showed bronchiectasis. And here again, first, this was the lymphocytes were gated on forward scatter and side scatter. Then we look at CD19. This is gated, so we have gated the B cells. And then within the B cells, we are looking for naive and memory B cells. And as you can see on the left hand side, that there are hardly any switched memory B cells, CD27 positive, they were 0.2 compared to 17% in the control. So the memory B cells are markedly reduced in the patient compared to the control, and this is consistent with a diagnosis of common variable immunodeficiency. Coming to the next category, congenital defects of phagocyte number, function of both. This is a 5-year-old boy, symptomatic since 3 months of age with recurrent pneumonia, recurrent fever, multiple episodes of pneumonia, recurrent skin abscesses. He again has anemia, severe anemia, slight leukocytosis with neutrophilic preponderance. Platelet count is normal. ESR and CRP elevated, and all the IgG, all the 3 immunoglobulin isotypes are elevated, and the FNHE showed granulomatous inflammation. And then when we did a DHR assay, so in DHR, what we do is that we take whole blood. Either you can take heparin or EDTA. It doesn't matter. You stimulate it with PMA, and then you first load it with a dry dye, which is known as dihydrorhodamine, and then stimulate with a stimulant such as PMA. And what PMA does is that it stimulates the neutrophil, and upon stimulation, the dihydrorhodamine is converted to rhodamine, and then there is a right shift. So in this patient, upon stimulation also, so this is the overlay showing the histograms in unstimulated and stimulated neutrophils, and you can see that there is hardly any shift in this. When compared to the control, you see there's a good shift to the right side in the stimulated neutrophils, and in the mother, you see there are two peaks. So even without doing a genetic diagnosis, you know that this is X-linked CGD, and so the gene genetic defect has to be CYBB, even without doing a genetic testing. And then this is again to show the control, and this is one of our patients DHR before uh, transplant, and then this is the patient after transplant. And you can see that after transplant there is a restoration of the neutrophilic function. As you can see, when the neutrophils were gated from this patient, they're showing marked right hand shift, indicating that the transplant has been successful and there has been restoration of neutrophil function. In addition to looking at DHR in CGD patients, you can also look at the different cytochrome, the NADPH oxidase components. So you can look at B558. So B558 stands for both GP91-FOX and P22-FOX. And in this patient, you can see there's a decreased in B558 compared to control. And this was a child with X-linked CGD. However, this can also be seen in patients with CYBA or CYBC1 defect. The next case is a 10 weeks old female infant who presented with delayed fall of umbilical cord with omphalitis. Again, she had anemia, marked leukocytosis of 73,000 with neutrophilic preponderance, and platelet count was normal. And when we look at this patient, you can see that the neutrophils were gated. And when we look at CD18, which stands for the beta-2 integrin, in the patient this was absent, confirming a diagnosis of leukocyte adhesion defect type 1. And this is another of our patients, just to show that in addition to CD18, you can also look for other markers like CD11A or 11B, and all the three, the CD11A, 11B, and CD18 were absent in this patient. So coming quickly to disease of immune dysregulation, this is a 2-year-old girl presenting with lymphadenopathy, hepatosplenomegaly, skin bleeds. She had ecchymotic patches over skin since 6 months of age, and she had severe anemia requiring multiple packed RBC transfusions. Pneumonia at 3 months, 3 years of age. She had anemia, leukocyte count was normal, differentials were also normal, but she had thrombocytopenia, and immunoglobulins were all elevated. And when we looked at the double negative T cells, so double negative T cells are CD3 positive, TCR alpha beta positive, and 4 and 8 negative. So this is the left, right quadrant. So you can see that the double negative T cells are 21%, which is markedly elevated. They should be less than 2.5%, and in this child it is markedly elevated. So this was a child with ALPS, and she had a mutation in Fas ligand gene. Normally usually the most common genetic defect is Fas, which could be a germline Fas or a somatic Fas, but in this child the defect was in the Fas ligand. Another clue was that in this child the serum Fas ligand was very low. It was nearly absent. It was 1.5 picogram against a normal of 55 to 180. In patients with Fas mutation, the Fas ligand is markedly elevated. So you can also look at perforin. So to look at perforin, you have to look at either the NK cells or the CD8 T cells, the cytotoxic T cells. So in this case, this is a child with perforin gene defect. And as you can see, the upper panel shows the control and the lower the patient. And in the patient, when we gated the CD3 negative, CD56 positive NK cells and looked at perforin expression, it was nearly absent in the child. This overload shows that this is nearly absent in the child compared to control, confirming a diagnosis of HLH because of perforin gene defect. The other test that we routinely do for HLH is a granule release test or a CD 107A degranulation. And in this child with HLH, the CD 107A was markedly reduced compared to control. The next category is defects in intrinsic and innate immunity. And the prototypic disorder in this is Mendelian susceptibility to mycobacterial disease. So IL-12 receptor beta 1, as I've said, is expressed only on activated T cells like CD154. This IL-12 receptor beta 1 can be seen only on activated T cells. So in this assay, we uh, separate the PBMC, stimulate with PHA for 72 hours, then we stain with CD3 and IL-12 receptor beta 1. And as you can see in the patient, this was decreased compared to control, confirming a diagnosis of MSMD because of IL-12 receptor beta 1 defect. Uh, there is another functional assay also. IL-12 receptor beta 1 could be normal, but when we look at p-STAT4, which is downstream of IL-12, you can see in the same patient uh, the p-STAT4 expression on gated cells was reduced compared to control. CD119 is a is IFN gamma R1, and in this child with IFN gamma R1 defect, autosomal recessive complete form, there was a nearly absent uh, IFN gamma R1 on monocytes, neutrophils, as well as lymphocytes. And also the p-STAT1, which is downstream of IFN gamma R1 and R2, this was also markedly reduced. In patients with the partial dominant form of IFN gamma R1, there is a increase in expression of IFN gamma R1 compared to control. It's a 1 log increase. So this is a partial dominant form where the IFN gamma R1, instead of being reduced, is increased. This is because of abnormal cycling of the receptor on the surface. Another assay which can be used for doing looking at the TLR functioning is the C62 ligand shedding assay. This was a child with IREC4 gene defect. And in this, it is opposite. I mean, when you stimulate, the shift is to the left, not to the right, because that molecule is being shed off. So in this child with IREC4 deficiency, you can see that the response to PMA and also to some extent and also to some extent LPS, the response was normal. But when we look at the response to TLR2 and TLR6 agonists, it is reduced, indicating that there's some defect in TLR signaling. So I will end here. I would like to acknowledge the clinical team and also the lab team at PGI, and also to my funding agencies for funding me for my work and research. Thank you very much. And also like to invite you all for the 7th International Conference on Inborn Errors of Immunity at Hyderabad in March. Thank you.
Thank you, Dr. Amit, for a wonderful lecture. It was enriching for all of us. It was beautifully crafted with so many cases, and you have shown us how versatile flow can be in evaluation of patients where you have a suspected phenotype. I am sure that the audience has understood that this is a very challenging field, and the expertise is located in very few areas. So thank you for sharing your time and your experience with us. Dr. Kirti, are there questions already available for Dr. Amit?
Yes, ma'am. There are few questions. Shall I proceed with the questions?
Yes, please.
So the first question is, which CD markers are basic to do lymphocyte subset analysis, and which other CD markers can be used for research purpose?
So for the basic lymphocyte subset analysis, you should have one gating marker, CD45, which is used for gating. Then you can have CD3 for T cells. For B cells, you can use either 19 or 20. For NK cells, you require both 15 and 56 and 16. And then if you also want to look at the helper and the cytotoxic, then in the same tube, you could add 4 and 8 as well. So I mean, like it depends on how much resources you have and to what extent you can do. But basic phenotyping, at least you should do TB, NK, and if possible, do helper and cytotoxic as well. That would be a basic panel. And then if you're in a pediatric hospital, doing a naive and memory would also be useful. And then if you're looking at something like CVID, then doing a B cell phenotyping would be useful. I mean, now actually there has been some shift of doing all markers together, like the in countries where more resources are available, you could do 12 or 13 colors in one go. Because in any case, if you find a defect one flow, you would have to proceed again to the third one, second one, third one. So I don't know. It depends on how much resources you have, what flow cytometer you have, and what kind of facilities you have. But for the basic panel, I think TB, NK, and if possible, T cell subset should be done.
So in your practice at PGI, where you have a very large in-house referral of patients with suspected IEI, what is it that you currently do
So
as a screening?
first we will do like TB, NK. So we'll use CD45, we will use CD3, CD19, 56, 16, and 4 and 8 maybe. HLA-DR we don't do routinely, although some people say that like, doing HLA-DR is also useful.
So
So
then
this
you
is
move on to further
so
testing
then
only based on.
yeah, we don't do a extended panel in all patients actually because it's not cost effective. Most of our patients cannot afford, because if you do like 12 or 15, 12 color or like maybe 13 colors in one go, that will be very expensive. It will be like 4,000, 5,000 per test. So it is very expensive.
So
And
I
it is
think I'll.
better to do like get antibodies on your own and then do it rather than, getting like pre-mixed cocktails which have got all the antibodies together. It is easier because you don't have to add individual antibodies, but it is more costlier. But if you buy individual antibodies and then do it, it will turn out to be cheaper because you can titrate the volume of antibodies that you have to use. I mean, you can use much less than the recommended antibodies.
The only concern there with some labs is that they say that the shelf life of these antibodies and the number of patients that get referred for diagnosis, that mismatch exists.
I think for the lymphocyte subset, this should not be a
Yeah,
problem.
subset is not a problem at all. It's only that the
And DHR is also not a very difficult, it is not very
yes.
difficult to standardize. You don't need very any fancy antibodies. You just need a DHR dye and PMA. But then you have to, I mean, like, you have to be very wise in how to, you have to make different aliquots of PMA because if you have taken it out once, it is gone. So what we do is that we make a working solution, we make a stock solution, which we keep it -80, then we make working solution, and then we aliquot from that. Because when we take it and we take out on the shelf for one reaction, it is gone. So, I mean, to aliquot each antibody, especially for DHR and things where activation is required, PMA and things like that, there you need some logistic planning and all that.
So I think to a large extent, because of the logistics of transporting samples for flow, as well as the widespread of
For
where
lymphocyte
patients with.
subset, it should not be a problem. I think lymphocyte subset 2 or 3 days also surface is not an issue. The problem is with the functional tests. For something like DHR, you can't do on like dead, because lymphocytes anyways have got very short half-life. So you can't do it on shipped samples. It will be very difficult. And interpreting it would be very difficult. You can have a control sample also. I mean, a travel, what we call a travel control. We have tried it within 24 hours, but the results are not as good as fresh samples. You can use a live dead marker, I mean, a dye which will stain only the live cells and then do it. Just one extra step or to improve on shipped samples, especially
Okay.
if doing a functional assay.
So we have one more question, sir. In your experience, how useful is flow cytometry in longitudinal monitoring of patients with PID? So longitudinal
As I
monitoring.
have said, I mean, like once the diagnosis is made, they will not. I mean, it will not be get corrected unless you've done a stem cell transplant, and then after stem cell transplant, no, they usually do it on a regular basis to look at engraftment. So, I mean, the routine use would be when the patient has before transplant and then after transplant to look at engraftment and to look at donor chimerism and things like that. But otherwise, I mean, routinely doing a flow would not be a very, I mean, you can do it. I mean, like, suppose if you have a patient who is very sick and then there are some issues that even sepsis might result in some alterations. Severe sepsis might result in alterations in different subsets and all. So you can do it once and then you can repeat it if you have any doubt after the acute episode of sepsis or maybe severe infection has resolved. Outside of this and of transplant, I don't think there is any logic. Protocol for longitudinally following up patients with flow cytometry.
Okay, so the
In patient,
similar. Yes, ma'am. Please continue.
in patients with CVID, do we have, CD27 positive B lymphocytes expanded or reduced? And would that be a screening?
CD27 is a marker for memory-based lymphocytes, and in CVID it is reduced.
So, does this?
It is also in one of the diagnostic criteria actually of
Yeah.
CVID.
So, is it also like reduced on T lymphocytes? Is it a marker for memory T lymphocytes also?
No, for memory, the marker for T is CD45RO.
Okay.
So CD27 is a marker for memory B lymphocytes.
Okay.
So one more question is like that, which we have discussed in previous question. Can we do this flow in severe infection when there is active infection?
So there is no point not to do it. I mean, you have to do it because, I mean, when the child is, for example, in SCID, the most of the children will come in like severe infections, and that might be the only opportunity to do that test and to confirm the diagnosis. If you have doubts, then probably you can repeat it, but there's no reason not to do it when the child is really sick.
Okay. So similar question like that. Can we assess vaccine responses in PID patients with flow?
So for vaccine responses, you will have to look at titers actually. I mean, flow is not a very flow can be used to look at the memory B cell response, or you can look at specific memory B cells. I mean, you can design a flow-based assay to look at a specific uh, memory B cells.
Antigen switched memory.
More easier would be to look at ELISAs for looking at. So, and also in like antigen responses, you have to look at two kind of responses to protein antigens and polysaccharide antigens. And in polysaccharide antigens, you could look at pneumococcal polysaccharide, but the problem with pneumococcal saccharide is that there are so many serotypes. So how many serotypes you test? So now we are not doing pneumococcal polysaccharide, we are doing the polysaccharide of Salmonella. So that is only one. So, and commercial kits are available. You can make in-house or you can do a commercial kits also available for the VI polysaccharide of Salmonella. So that you can do for testing for polysaccharide. For protein, you can look for diphtheria or tetanus.
Okay.
That will be easier than designing a specific. I mean, you could do by even by things like ELISpot or something like that, where you look at antigen. I mean, B cells which are specific to a particular antigen, but that would be more complex and cumbersome. A simple way would be to look at for a protein response to protein antigen or protein vaccine would be to look at response to diphtheria or tetanus, and for a polysaccharide to look at VI polysaccharide.
Okay, sir. So the next question is that can we replace genetic tests with flow for IEI in near future? Is it possible?
No, I mean, each has its own role. I mean, you can't replace one with the another. I mean, we think that NGS aa gaya to sab kuch, like, why do we need flow cytometry? But we do need flow cytometry because, I mean, like, this is a high
Under
technology to throw you so many variants of undetermined significance where you don't have any functional defects. So, at least for immunological diseases, we have got a good handle. I mean, we've got like immune cells. We don't need those fancy tests, which, I mean, patient with other genetic defects, you might require cell lines and stuff like that. But here you have got at least the patient's blood cells, which you can test functionally for different functions. So there is the relevance of flow cytometry. I mean, to validate, like if you've got a view as, like for example, I remember that we had a patient where we were suspecting hyper IgE syndrome, but when we did the in-house NGS panel, we got a variant in CYBB gene. And so we were quite surprised, and because it didn't fit with CYBB. But when we did the DHR was perfectly normal. So that means, and that variant had not been reported earlier. It was a rare variant. and we had no information. Now, actually, that variant has been classified as benign on ClinVar, but at that time there was no information about that variant. But because we did the DHR and we found that the DHR, I mean the functionally that variant had no impact on the neutrophil function, we could safely say that this is a benign or a likely benign variant. So I mean, like, each one has its own role. I mean, one can't replace the other. They're complementary.
Okay, sir.
But in situations of emergency, you should not wait for, I mean, like the genetic diagnosis to start treatment. If you're suspecting antibody deficiency, irrespective of whether you're getting a genetic defect or not, you would still uh, start IVIG. And similarly, if a combined defect is there and you're waiting for transplant, you would still start IVIG and start doing HLA typing and stuff like that, so that you work up the child for a potential hematopoietic stem cell transplant.
Okay, sir. So
And
one
genetic
comment from
diagnosis would also be required for, if you want to offer prenatal diagnosis or antenatal diagnosis to the family. What often happens is that in SCID, these families, they lose their children and then they come back again in the next pregnancy, and then they want to know whether this child is affected or not. So if we have a genetic diagnosis, it is very easy. You have to look at one genetic variant in the fetus, and then you can be sure whether this fetus is affected or not. Based on flow cytometry, it's very difficult to do that. I mean, it is not also indicated. You have to have a genetic defect uh, in the proband and the index patient to do it in the for prenatal antenatal diagnosis. And also in this rare disease policy, in some centers, they want a genetic defect to before they start, they provide any support or treatment. That is also coming up as another issue, because what a lot of our patients with CVID who are at other centers, they're saying that in absence of genetic defect, even if they show that they have CVID, they're not getting treatment. And in countries where there is insurance, that will also be a problem. I mean, like they need some sort of a genetic diagnosis to.
Okay, so this one comment from Dr. Vignesh sir is many of CVID do not have genetic etiology at present.
Yeah, that's what I was alluding to. And
So
these
that's
patients,
important. Yeah.
especially in some centers, they are not, they are being denied IVIG. They're saying that this is not a genetic, this doesn't come under rare disease. That's what they're being told.
Okay, so this last question is about ALPS. Double negative T cells less than 2.5%, is it mandatory for diagnosis of ALPS?
So the
No,
double negative T
that
cells
is
expanded.
more than actually, not less than.
Oh, yeah, more than.
It is one of the diagnostic criteria.
So if it is normal, can we diagnose ALPS?
I mean, the likelihood of it being ALPS would be very low.
Okay. And then how to proceed with the somatic FAS mutation?
So if you're doing an exome, the coverage would be typically like maybe like 40 to 60x. And in that case, picking up a somatic variant would be very difficult. Either what you can do is you can sort the cells. What people do is they sort the double negative T cells. You have to sort the double negative T cells and then look at the genetic mutation in those sorted double negative T cells. Got my point. So you have to sort the double negative T cells by flow cytometry and then extract the DNA from the sorted cells and then look at the mutation. That's the one way of doing the somatic fast. The other way is that you do a panel with a very high coverage. I mean, you do a panel which like maybe like 1,000 or 2,000 coverage. There, if you look at a very low variant allele fraction, like VAF of maybe like 4%, 5%, maybe you could find there if you have got a very high coverage. I mean, the sure shot way would be to sort the double negative T cells, extract DNA, and then screen for the genetic defect in those DNA from the sorted cells. The other possibility would be to do a very high coverage panel and then look at the FAS defect. But then you have to not put a filter. Normally, for germline, we put a filter of 15 to 20%. उससे कम variant हटा दो. But in this case, you have to be very cautious that you have to lower the threshold so that you pick up variants. Because if you're looking at somatic variant, it will be present at a very low variant allele frequency. So in that case, you have to put a low threshold for calling a variant. Those are the two ways that you can go about looking at a somatic class.
Okay, so that is the last question. So thank you, sir.
Thank you, Dr. Amit. I think each one of us has learned a lot from your lecture. When I'm thanking you once again for sparing your time so generously with us. Thank you.
Thank you, ma'am.
Thank you.